Today we're going to be taking a look at a few theorems that deal with angles inside polygons. Now remember, a polygon is an enclosed figure with straight sides is a good way to think about what a polygon is. So like triangles and rectangles and squares are examples of polygons. But then a polygon could have really any number of sides. So if it had 5 sides, we'd call it a pentagon. 6 sides, we call it a hexagon. At some point, we just call them n-gons, where n is the number of sides on that polygon. So like a 13-sided polygon, we just call it a 13-gon. But we're going to be looking at those polygons, and we're going to be looking at a couple theorems having to do with their angles, both their interior angles and their exterior angles. So let's jump right in. To start off, I just want to remind you of a couple things, or really one thing just for right now. We need to remember that if we have a triangle, like I have here, and it has 3 angle measures, A, B, and C, that we know that those 3 angle measures will always end up being having a sum of 180 degrees. So it doesn't matter what the triangle looks like. If I add its 3 interior angles together, I'm always going to get 180 degrees. Now that's important because if I look at something like a quadrilateral with 4 sides or a pentagon with 5 sides, they would not have totals that add up to 180 degrees. You could probably even look at that and say, you know what, I think that's going to end up being more than 180 degrees. And the way that we're going to try and figure out in general what the total number of degrees for the inside angles in a polygon will be is we're going to use this idea of a triangle's angles adding up to 180. Because if we look at this quadrilateral, we could draw one segment in the middle of this quadrilateral, something like this, and that one segment would break that quadrilateral into 2 triangles, right? And so I could look at those 2 triangles and I could say, all right, now this one, those 3 angles, A plus B plus C, are going to equal 180. And then if I had x, y, and z degrees for this other triangle, I would know that x plus y plus z would equal 180. And so if I was looking at the total of all these angles for my triangle, or for my quadrilateral, I could add b plus z plus the combination of c and y plus the combination of a and x. So in other words, if I wanted to find the total for the inside angles of this quadrilateral, I'd be adding a plus b plus c plus y plus z plus x. So I'd be adding these 2 amounts together, and I would get a total of 360 degrees. So my 4-sided shape has a total interior angle measure of 360 degrees. Now if we come to my 5-sided shape and I kind of do the same thing, I'm going to draw a line connecting these 2 corners, and then I'm going to draw another one connecting these 2 corners. I could do a little bit better job there. There we go. And now I have 3 triangles. So if I label the inside parts of those 3 triangles, I'd have A, B, and C degrees, and I know that A plus B plus C would equal 180. And then I'd have D, E, and F degrees, and I know that D plus E plus F would equal 180. And then I could have, let's say, on this 3rd triangle, G, H, and I degrees, and I know that G plus H plus I would equal 180. So if I was trying to figure out the total for all 5 angles of my pentagon, I'd be adding A plus B plus E plus F plus I plus plus H plus G plus D plus C. So I'd be adding all of these letters together, and as I can see, if I add all these together, I'm going to have a total that's 180 plus 180 plus 180, right? And I would have eventually a total of 540 degrees. So I'd have 540 degrees for my 5-sided, right? That's if it has 5 sides. I'd have 360 if it has 4 sides, and I'd have 180 if it has 3 sides, right? 180 if it has 3 sides. So now I can start looking at maybe there's a pattern here. I could maybe make up a little table here. I'm a little bit short on space on this page, but I think we could squeeze it in somewhere. That if I'm looking at number of sides and then total interior angles, I could kind of do a little bit of a table here, and I could say, okay, when it had 3 sides, there was 180 degrees. When there was 4 sides, there was 360, which is 180 times 2. When it had 5 sides, it had 540 degrees, which we found out is 180 times 3. We could probably make a prediction where if it had 6 sides, we could think that it's probably going to have, oh, let's see, a 180 times, I had 180 times 1, 180 times 2, 180 times 3. 6 sides seems like it would be 180 times 4, which would be 720 degrees. All right, that's 180. That is 180 times 4. And from that, we could maybe say, well, what if it had 10 sides? I wonder what a polygon with 10 sides, what its total number of interior angle degrees would be. And I might say, all right, it would be, I could keep this pattern going and saying, okay, for 7 it'd be 180 times 5, for 8 it'd be 180 times 6, for 9 it'd be 180 times 7, and for 10 it'd be 180 times 8. Or I could notice that I'm always multiplying 180 by a number that is 2 less than the number of sides. Here it was 180 times 1, and that's 2 less than 3. Here it was 180 times 2, and that's 2 less than 4. Here it was 180 times 3, which is 2 less than 5. So I think that if I was doing 10 sides, let's just come down here and say 10 sides, that would probably be 180 times 8. And if I was doing 43 sides, I think that would be 180 times 41. Right? And so no matter what number of sides I'm dealing with, I think I could find the total for the interior angles by just taking 180 times the number of sides minus 2. And so that idea actually takes us to our first theorem for this video. It's called the Polygon Interior Angles Theorem, and it says just what we just discovered, that the sum, remember sum is when we total up using addition, the sum of the measures of the interior angles of a convex n-gon. When it says convex there, that's just specifying that it can't be concave. And like for instance, a concave polygon would look something like this, where one of these angles here is kind of like, it's kind of pointing into the middle of the shape. We won't be dealing with many convex polygon, or sorry, concave polygons in this class. So pretty much everything we're going to deal with is going to be concave. So you don't have to worry too much about that word. I just want to kind of explain what it meant. But anyway, going back to the theorem, it says that the sum of the measures of our interior angles of a convex n-gon, where it has n number of sides, is going to be 180 times n minus 2. So we're going to take the number of sides, take off 2, and multiply by 180. So for instance, I see here that I have 7 sides. I also have 7 angles. Important to remember that the number of sides and the number of angles in our polygon will always be equal. So they've labeled the 7 angles of this polygon, which means it has 7 sides. And if we wanted to figure out what all of those angles add up to, we can just take 7 minus 2, which is 5, and multiply by 180 and get 900. Now the next thing we're going to look at is called a corollary. A corollary is kind of like an addendum or like an added part. It's like a part 2, if you will, a sequel. And so the corollary to theorem 6-1, it's not its own theorem necessarily, it builds off of theorem 6-1. It says that the measure of an interior angle, so one interior angle, difference here is we're talking about one interior angle, of a regular n-gon. Now remember that a regular shape has all angles congruent and it has all sides congruent. All right, so if we're looking at one of the angles inside a regular n-gon and we want to know what its measure is, we're going to find the total of the angles. So that's the top part of this little formula here. We're going to find the total of the angles by taking off the number of sides minus 2, multiplying by 180, and then we're going to divide by how many sides there are. So as an example, if we have a 5-sided regular polygon, so this would be a regular pentagon, it has 5 sides that are all the same length and 5 angles that are all the same, and I want to know what one of these angles are, I could take 5 minus 2 times 180, so that would be If I just kind of simplify this little theorem here, or this little formula, that would be 540. And then if we divide that 540 by 5, we'll get 108 degrees for any one of these angles. And again, that only works for regular polygons. If my five-sided polygon looked more like this, okay, so this is not a regular polygon, not a regular pentagon. Doing this would not tell us the measure of any of these angles because we don't really know much about those angles. It looks like they're all probably different measures. But when we know that it's a regular polygon and we want to know one of these angles, we can kind of do this calculation right here. Now there is one more theorem that we're going to take a look at, and that's called the exterior angles theorem, or theorem 6-2, the exterior angles theorem. Now we know that if we're dealing with exterior angles, okay, we've done exterior angles of a triangle before, so if I sketch out a triangle here, and then if I extend each side, then that extension created 1, 2, 3 more angles. And we know that in my exterior angles of a triangle theorem, I know that this angle here is supplementary to this one inside. I also know that it's equal to these other two remote interior angles added together. So if I put values of like A, B, and C on here, I would know that angle 1 is equal to either 180 minus C, or I know that it's equal to A plus B, right? And angle 3 would be 180 minus B, or we could say that it's equal to A plus C, and angle 2 we know is going to be 180 minus A, or it's going to be equal to B plus C. That's all stuff that we knew from before. But now we're interested in knowing, well, what if I add angles 1, 2, and 3 up? And what we find out is that when we do that, when we add up the exterior angles, if we're doing 1 at each vertex, then what we'll get is always going to be 360. And so if it's a triangle, angles 1, 2, and 3, they're going to add up to 160 in this triangle. If it's a pentagon, like I have over here, angles 1, 2, 3, 4, and 5 always add up to 360. So it doesn't actually matter how many sides we have. If we want to find the total of the exterior angles of our polygon, and it doesn't matter whether it's regular or not regular, if I add up the exterior angles, I'll always get 360, no matter how many sides or angles my polygon has. And there's a proof to this one, but I'm not going to take the time in this video to go through it. It's a little bit more complex, a little longer. But it works out mathematically that will always happen no matter how many sides you have for your polygon.